Here we're going to talk about the wind circulation, how air is flowing across the planet. And for our first aspect, the key thing we're going to describe this is going to say that pressure differences generates the wind. So let's go ahead and cut over to a demo showing the relationship between temperature and pressure. Here we're going to look at the relationship between pressure and temperature, and I'll take a nice pre-filled balloon that has a constant volume in it. So I can't change the volume in the balloon, but I can change the temperature and see how the pressure correspondingly changes. In this dewar here, I've got a nice big pool of liquid nitrogen. So let's go ahead and put this guy in. And for reference, balloon just the right size to fit in the dewar. Let's go ahead and chill it now. Just dip it in that liquid nitrogen and just let the balloon change in size. A little more. Get it nice and cold. And now it's a deflated balloon. A lot more space. So the volume, specifically the volume's constant, but the pressure will change. There's less pressure in the balloon now. Chill it some more. As soon as I pull it out, it starts heating back up to room temperature. You can almost see it there, reinflating. Back in the liquid nitrogen, chill. Let it deflate. Let the pressure go down. The pressure going down is the crucial part. Once it starts to heat up again, the pressure can go up. The balloon can expand in size. So there's this relationship between the temperature of the object and the pressure of the gas. So now connecting this pressure equals winds idea, we can finally describe this Hadley circulation. And this is the process of how warm air is transported across the planet. So in this simple model here, the equator is going to be the hottest. The equator is getting luminesced by the sunlight the largest amount. So the warmest air you're going to find on the planet is up here around the equator. Now, through processes of convection, that hot air is going to rise, and with the Hadley sail, this whole thing here is what we mean by the Hadley sail, this Hadley circulation. That warm air rises. That warm air is creating a pressure difference, right? We have cold air here at the north and south poles, and that cold air, lower pressure, will then start to push out, right? That temperature change. There's less pressure here. This hot air will push this. So the cold air gets pushed out. Cold air approaches the equator. He mixes with the hot air and repeats. So this cell itself is building up how the global winds are created. In the previous slide, I said this was a simple model, and we should expect that. We should expect something to be a bit more complex, because these Hadley cells are just going from the poles to the equator and back. But we know of things like the trade winds, the westerlies and the easterlies. So where are those coming from? Well, it's because the Hadley circulation, these pictures that we're looking at here, this rotation here, this is only a picture of what the wind patterns would look like if the planet wasn't rotating. But now we have to introduce that. So on a stationary, non-rotating planet, we'd have these two very simple Hadley cells. But now put a rotating planet into the picture and see what happens. So let's add some angular momentum, get the planet spinning as we expect on where we live, and discuss what happens to the air that's moving. Now, these bullet points here, they refer to any air that's moving in a northerly direction. So, consider this red arrow, right? You have air here moving in a northerly direction due to whatever wind patterns are happening at that time. If that air is moving northerly, the rotation of the planet will deflect that to the right. Correspondingly, if you go to the southern hemisphere, once again, it's this arrow here that I'm talking about. This air is going northerly but it's in the southern hemisphere? Well, because of the rotation of the planet, this south hemisphere northerly moving air, try saying that 3 times fast, will be deflected to the left. So the resulting pattern is that you have, say, storm patterns in the northern hemisphere that are always rotating in a counterclockwise direction, whereas in the southern hemisphere, they'll always rotate in a clockwise direction. That flipping, this asymmetry caused by the flipping crossing the equator, is due to the rotation of the planet. The way that the winds break between northern and southern hemispheres, can be described in what's called the Coriolis Effect. And the Coriolis Effect describes the motion on a rotating body. You sometimes might hear phrases like Coriolis forces, how they are pseudo forces or not real. And the simplest example I can give you is one that I've used before, and it's when you are in a vehicle, you're moving very quickly, say 60 miles per hour, 100 kilometers an hour, something like that, and you turn the wheel, and all of a sudden you or your items in the car slide into the door. This is related to those Coriolis forces. So that effect of this force that comes out from turning, this turns into a conversation about your reference frames that you're using. So I'll keep this simple and basically say that when you live on a rotating object, you'll have these Coriolis effects. In terms of wind patterns, it takes that, let's go ahead and draw it. It takes that Hadley cell that we initially shown. The initial Hadley cell we showed did this kind of pattern. So that was our initial Hadley cell, our Hadley circulation on a non-rotating planet. Well, the Coriolis effects breaks this cell here into these smaller ones, these smaller components. And that's how you get your trade winds, your easterlies, and your westerlies throughout the planet.